Hello everyone. As informed, we will be solving with the numericals. In this session, I will be starting from the first unit, first 2 units I am taking, which includes chapter 1 and 2, electric charges and fields, and also electric potential and capacitance. From that, I have chosen the first question. It is asked in March 2014 examination. So let's solve this. It says in a parallel plate capacitor with air between the plates, each plate has an area of, so observe here, they talk about a value and it is area of 6 into 10 to the power minus 3 meter square, and the distance between the plates is, so distance between the plates is 3 millimeter. Distance between the plates is 3 millimeter. Calculate the capacitance of the capacitor. So the first one we need to calculate is capacitance of the capacitor. Later, if this capacitor is connected to a 100 volt supply, so we are connected to a 100 volt supply, then what is the charge on each plate of the capacitor? That's the second part of the question. So first, let's calculate the capacitance of the parallel plate capacitor, and here this says specifically air between the plates. So dielectric constant for air is equal to 1. We can make use of the, let's collect the data. Let's follow the basics. Area of 6 into 10 to the power minus 3, that is A 6 into 10 to the power minus 3 meter square. We can find out the quantity if the wordings you feel very difficult to find out the quantity through wording. So look at the unit. If you have a look at the unit meter square, obviously it has to be area. So by this method also you can find out which quantity they have given. And the distance between the plates is 3 millimeter. Distance that is represented with D. So that is 3 millimeter. Millimeter is not the SI unit of distance. So the standard SI unit of distance is meter. So milli 3 into 10 to the power minus 3 meter. So we need to be very conscious when we are taking the values. If you won't convert it to meter, so the entire value is going to be wrong. So let's 3 millimeter is 3 into 10 to the power minus 3 meter. We are here already in the question. Calculate the capacitance of the capacitor. Capacitance is represented by C, which we need to find the first part of the question. We have collected the data. Have a look at this. Is how these three quantities are related. Let's find out how these three quantities are related. So we will get an equation. Capacitance is related as C is equal to A epsilon naught by D. So this is the formula. C is equal to A epsilon naught by D. You can also use C when we have dielectric. K is equal to K A epsilon naught by D. Here I am avoiding that because they say in parallel plate capacitor with air between the plates. So it's air between the plates, air is there. So K is equal to 1. I can go with this equation directly. This epsilon naught. A is 6 into 10 to the power minus 3. Epsilon, the value of epsilon is 8.854 into 10 to the power minus 3 farad meter. Epsilon is permittivity of free space. Then D, 3 into 10 to the power minus 3. Let's solve this. To the power minus 3, sorry, 8.854 into 10 to the power minus 12 it is. 10 to the power minus 3 in the numerator we have 10 to the power minus 3. They cancel out. Here it's cancelled out. This 1s are 2s are. So let's find out. 2 into 4, 8. 8, 10, 0, carry 1, 16, 17 and carry 1, 2 8 is 16, 7, so 17.708. We have 10 to the power minus 12 here. So let's place it 10 to the power minus 12. The SI unit of capacitance is, it is farad. Okay, if you cannot able to remember the SI unit of farad, so they will be giving the units at the end of the quantity. They might give S naught is equal to 8.854 into 10 to the power minus 12 farad meter. So it is going to be, one second, farad per, let me cross check. Meter square meter farad, I have to get, if it becomes per meter only, I will let, so it is going to be farad per meter. So you can, in this way also you can find out the SI unit of capacitance. So get the capacitance, C is equal to 17.708 into 10 to the power minus 12. Okay, this is the first part of the numerical. Still I can say we have done it up to 3 marks. Still we have a second part, that's for 2 marks. If this capacitor is connected to a 100 volt supply, so that is voltage V is equal to 100 volt. Then what is the charge on each plate? That's Q. We need to find. So that's we have calculated the capacitance. So this capacitor is connected to 100 volt supply. What is the charge? What is the relation between Q, V and C? It's very simple. Q is equal to CV. So C is 17.708 into 10 to the power minus 12 into 100 into 100. So I can write as 17.708 into 10 to the power minus 10. Because 10 can be written as 10 to the power 2. So minus 12 plus 2 will be minus 10. This value is not going to change anything here. So I can write as 17.708 into 10 to the power minus 10 coulomb. This is coulomb. So charge on each plate of the capacitor is going to be 17.708 into 10 to the power minus 10 coulomb. So we are done with the question. We wanted to calculate the capacitance of the capacitor, so that we get it as C is equal to 17.708 into 10 to the power minus 12. You can also write this value is 17.708 picofarad. See, 17.708 picofarad, because pico refers to 10 to the power minus 12. So, and we can calculate the charge as 17.708 into 10 to the power minus 10 coulomb. Right. Let's go for the next question. Let's move on with the second question from first 2 units. This question is asked in July 2014. That's all this. 2 charges, 3 into 10 to the power minus 8 coulomb and minus 2 into 10 to the power minus 8 coulomb, 2 charges, are located 15 centimeter apart. So let's draw it. So I take 3 into 10 to the power minus 8 as Q1. So Q1 is equal to 3 into 10 to the power minus 8 coulomb. And another one, Q2, that is Q2, the second charge I call it as Q2, minus 2 into 10 to the power minus 8 coulomb, are located 15 centimeter apart. Let's say the distance between them is, as they give, 15 centimeter So in this problem, what you can do is you can convert it into meter here itself, or on solving this numerical, finally we can convert it to the meters. Both the ways are allowed. So we have two charges Q1, Q2 are located at 15 cm apart. At what point on the line joining the two charges? At what point on the line joining the two charges is the electric potential 0? So at what point on the line joining the two charges the electric potential will be 0? So there will be 2 points. There will be 2 points at which the electric potential will be 0. One between the two charges. One between the two charges, and one more information I would like to give you is the electric potential will be 0 always near to the smaller charge. Let us say this point P. One point where the electric potential is 0. The another point out of these two lines, and it is also near to the smaller charge. So you can call this as point 1 and this as point 2. This point 1 and point 2 where the electric potential is 0 is always near to the smaller charge. So let's find out P1. For this what I do is I consider this P1 as P1 at a distance of x from Q1. Call this distance as x, and the remaining I can call it as 15 minus x in centimeters. So I am calculating it for the first one. So x, the remaining distance will be 15 minus x, that's the distance from Q2 to point P1. So the electric potential at point P1 will be due to charge Q1 and Q2. We know that it obeys superposition principle. That is, the total electric potential at point P1 is the electric potential due to Q1 plus electric potential due to Q2. So I can call it as, for first case, potential at point P1 is equal to potential due to charge Q1, I call it as V1, plus potential due to charge Q2, that is V2. The potential at point 1 Vp1 is equal to V1 plus V2. Our intention is here that we need to find out that where is the point P1, or else we need to find out x here in this situation. Let's do that. Vp1, so here the potential is 0. So that is Vp1 is equal to 0, which is equal to V1 1 by 4 pi epsilon, I take it as k 1 by 4 pi epsilon into Q1 whole divided by the distance x plus k into Q2 divided by the distance from point P1 to Q2 is 15 minus x. So let's substitute the value. 9 into 10 to the power 9, Q1 3 into 10 to the power minus 8 whole divided by x as it is, I write, plus k 9 into 10 to the power 9 Q2, that is minus 2 into 10 to the power minus 8. So we have to, if the charge is negative, you have to take it as negative. In case of potential, in case of field, if you are discussing, it has to be positive. Let's restrict. If charge Q2 is negative, in case of potential, we take it as negative. The distance of P1 from Q2 is 15 minus x. So this entire value is negative. I take it onto this side, so it becomes positive. Plus into minus is minus, so I take this value to this side. So what happens? 9 into 10 to the power 9 multiplied by 2 into 10 to the power minus 8 whole divided by 15 minus x, which is equal to this remaining value 9 into 10 to the power 9, 3 into 10 to the power minus 8 whole divided by x. So let's solve this. 10 to the power minus 8, 10 to the power minus 8, 10 to the power this entire value cancel out. I'm left with 2 by 15 minus x, which is equal to 3 by x. On cross multiplication, 2x is equal to 15 into 3, 45 minus 3x. I send this negative value minus 3x to this side, it becomes 5x is equal to 45. X is equal to 45 by 5, that is 9 centimeters. So you can convert it to 9 into 10 to the power minus 2 meters. So you see 9 centimeter. So the point P1 is at a distance of 9 centimeter from charge Q1. So 9 centimeter means it is near to the smaller charge at a greater distance from the bigger charge. In the initial I said the potential will be 0 at a point where it will be near to the smaller charge, so it is also satisfying our answer. So this is the first point where the potential is 0, first case. And there will be another point which is out of the two charges, that is somewhere here. This is also the line joining the two charges. Let's find out the second point where the potential is 0. That is second case. Let's solve here. VP2. So I call this one as V1. First, let's find out the distances. P2. I call this distance P2 from Q1 as x. P2 is at a distance of x from Q1. This Q2, so x minus 15. P2 is at a distance of x minus 15, so that will give us this distance. If I subtract x minus 15, I will get the distance between Q2 and the charge, charge Q2 and point P2. So this distance is x minus 15. Okay, so let's calculate the required value. So at point P2, the potential is Vp2 is equal to V1 plus V2, and Vp2, the potential is 0, that is Vp2 is equal to 0. Then I get 0 is equal to V1, that is K Q1 divided by x. Since this is the distance, this P2 from Q1 is at a distance x, that's why I am writing here, plus K Q2 divided by x minus 15. So let's substitute the values, and as one more thing we can do, I take this, since Q2 is negative, I take this onto this side. So what happens? K Q2, that is minus of x minus 15 is equal to K Q1 divided by x. So K gets cancelled. Let's substitute the value. Minus of Q2 is minus 2 into 10 to the power minus 8 all divided by x minus 15, which is equal to 3 into 10 to the power minus 8 all divided by x. So minus into minus plus 10 to the power minus 8, 10 to the power minus 8. On cross multiplication, this will be 2x is equal to, this goes there, 3 into x is 3x minus 45. So 45 I take this side, it becomes plus 2x onto that side. So minus, what I get, 45 is equal to, sorry, 45, x is equal to 45 centimeter. Or you can also call it as 45 into 10 to the power minus 2 meter. So I can say this point P2 is at a distance of 45 centimeter from Q1. P2 is at a distance of 45 centimeters from Q1, and at that point the potential is 0. At that point, the potential is 0. So what was our intention? The aim of this numerical is, we have two charges separated by a distance of 15 centimeter. So we need to find out the points where the electric potential is 0. In this case, there will be 2 points. There will be 2 points, one between the two charges and another one out of the two charges. And remember, these 2 points will always be near to the smaller charge. Will always be near to the smaller charge. You can say 9 centimeter from X. So from Q1, this is at 9 centimeter. So the remaining is 6 centimeter. So for Q2, this point P1 is at a distance of 6 centimeter. And let's say the X is, in second case, we get it as 45 centimeter. If you find that distance from Q2, 45 minus 15, 30 centimeter. So remember this point, the potential will be 0, always near to the smaller charge when we have two charges. So let's proceed for the next question. Here we have the question number 3 from the first 2 units. The question says 2 point charges plus 1 nanocoulomb and minus 4 nanocoulomb are 1 meter apart in A. So we have 2 charges. We have 2 charges plus 1 nanocoulomb and minus 4 nanocoulomb. I can take it as Q1 is equal to plus 1 nanocoulomb. Nano, that is 1 into 10 to the power minus 9 coulomb. And Q2 minus 4 nano coulomb, so that is minus 4 into 10 to the power minus 9 coulomb. So Q1, Q2 are 1 meter apart. That means 2 charges are placed 1 meter apart. Let me write that diagram here. So this is our Q1, 1 into 10 to the power minus 9 coulomb, and let's say this is Q2, that is minus 4 into 10 to the power minus 9 coulomb. The distance between them is 1 meter. Okay, 1 meter. This is the question. Find the positions along the line joining two charges at which the resultant potential is 0. So this question is asked in March 2015, which is similar to the question to what we have discussed earlier. So here also we have two charges separated by a distance of 1 meter, and we need to find the points, find the positions along the line joining two charges at which resultant potential is 0. So let's find them. There will be one point between the two charges. There will be another point away from the two charges. And as we know, that point will be near to the smaller charge. So the first point where the potential is 0, I say it as somewhere here. This is P1. So when I write this, the first question will be coming into your mind is that, so minus 4 is smaller compared to the 2. But actually, you see, this 1, minus 4 is smaller compared to 1, but actually minus 4, the minus refers that there are more number of negative charges. The negativity always refers more number of negative charges. Positive refers deficiency in negative charge. Positive refers deficiency in negative charge. So in that case, I say this minus 4 or Q2 is greater than Q1. So the point will be here near to the smaller charge. The other point will be on this side of Q1. So let us call this as P2. So first let us find out P1, case 1. I call this as X from Q1. In the first case, let us say the point P1 where the potential is 0, which is at a distance of X from Q1. The remaining will be the distance of P1 from Q2 will be 1 minus X. This entire 1 minus X, so will be the remaining distance. So let's find out the potential point P1 where the potential is 0. So for this case 1, that is Vp1 is equal to V1 plus V2. V1 is potential at P1 due to Q1. V2 is potential at P1 due to Q2. As they obey superposition principle. So Vp1 is the point where potential is 0. That is, since Vp1 is equal to 0, which implies V1 plus V2 is equal to 0. Let us say V1 is equal to V2 or minus V2. Yes, this is going to be minus V2. Let's substitute the values. K, Q1, the denominator will have distance of P1 from Q1, that is x, which is equal to K is minus K Q2 whole divided by 1 minus x. K and K gets cancelled. Let's substitute the values. Q1 is 1 into 10 to the power minus 9 divided by x, which is equal to minus of minus 4 into 10 to the power minus 9 coulomb whole divided by 1 minus x. So minus 9 minus 9 minus 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 into minus plus, on cross multiplying I get, which implies 1 minus x is equal to 4x. 1 minus x into 1, that is 1 minus x, 4 into x, 4x, x I take down to that side, that becomes 5x. So finally I get x is equal to 1 by 5 or 0.2 meters. The point P1 is at a distance of 0.2 meters from Q1. So initially what I informed you, the point potential will be 0 near to the smaller charge. You see, the total distance between two charges is 1 meter. We assume that it is near to the smaller charge, the point P1, and we call it as distance x, and we are getting 0.2, so our assumption is right. So we get the point P1 is at a distance of 0.2 meters from Q1. If they specifically ask what is the distance of potential 0 from second charge, so you can say 0.2, 1 minus 0.2 is 0.8. You can also write the point potential at 0.8 meter from charge Q2. So we are done with the first case. Let's solve with the second case, that is P2. So I call this distance from Q1 as x. From Q1, the point P2 is at a distance x. And from Q2, the distance from Q2 will be, what happens, x plus 1 meter. So this entire distance, I take it here, sorry for the inconvenience. This entire distance, that is P2 to Q2, will be 1 plus x. This is the distance from here to here, 1 meter plus x. So the total distance of P2 from Q2 is 1 plus x. Let's solve this. Okay. So second case, Vp2 is equal to V1 plus V2, and Vp2 is the point where the potential is 0. That is, since Vp2 is equal to 0, so V1 plus V2 is equal to 0. This I write it as V1 is equal to minus V2. So K Q1 divided by V1, that's the potential at point P2 due to charge Q1. So the distance is x, which is equal to minus of K Q2 whole divided by the distance of point P2 from Q2 is 1 plus x. K on this side, here they get cancelled. Q1, what we have 1 nanocoulomb, that is 1 into 10 to the power minus 9 divided by x, which is equal to minus of minus 4 into 10 to the power minus 9 or divided by 1 plus x minus to minus plus 10 to the power minus 9 10 to the power minus 9. So on cross multiplying, what I get, 1 plus x is equal to 4 into x, 4x. So x is taken on that side, 1 is equal to 3x, and finally x is equal to 1 by 3 or 0.33 goes on meters. So 0.33 meters. So from Q1, the point P2 is at a distance of 0.33 meters. If you want to know it from Q2, so it is 1 plus 0.33 meters.